Hello, my name is Victor Lopez from Northwestern University, and it's a pleasure for me being in this Congress, sharing my last results in the electrical manipulation of metallic antiferromagnets that I'm developing in the group of Professor Halili at the Northwestern University. Antiferromagnet materials, now it's a hot topic in spintronics due to the possibility to fabricate and obtain new, fast, scalable, memory and high frequency devices. To accomplish these goals, we need an effective method to manipulate the antiferromagnetic state. And one of the most studied to date is the spin orbit torque. And based on that, we can distinguish two main kind of devices that people is studying. So those ones where are based in antiferromagnets that possess an intrinsic spin orbit torque, as the case of broken inversion symmetry antiferromagnets like copper manganese arsenide and gold manganese, where when we apply electric current through these materials, due to the broken inversion symmetry, exists a finite spin orbit torque that it's able to switch the Snell vector and then change the electrical resistance of the device. Here you have two examples with copper manganese and gold manganese. In the case of antiferromagnets, like the insulating nickel oxide, it's possible also to manipulate the antiferromagnetic state by an intrinsic spin orbit torque that, for example, in this case, if we sandwich the nickel oxide between two platinum layers, when we apply electric current through the platinum or the heavy metal, we generate a finite spin orbit torque, a spin current that diffuses inside of the antiferromagnet that also it's able to manipulate the antiferromagnetic state. Although these results are very important and pave the path through a new antiferromagnetic spintronics, broken inversion symmetry materials are very complicated to construct. Usually they are fabricated using molecular beam epitaxial techniques, so they are not compatible with current semiconductor technology. That the construction method preferred by the industry is sputtering. And in the case of materials combined with heavy metals, as the case of the nickel oxide, the density current that we need to effectively change the antiferromagnetic state and read it by electrical means is still too high. It's the order of 10th of megaamps per square centimeter. So based on this, we propose a new kind of devices based on metallic antiferromagnets, because these materials has lower exchange constant, and then in principle, we will need a lower density current to change the antiferromagnetic state. So we focus on work in the manganese antiferromagnetic family, in particular in platinum manganese and iridium manganese. And another reason is because those materials are extensively used as a source of exchange bias and spin orbit torque in magnetic memories, as the case of MRAM and sensors. So these materials can be sputtered, and then they are compatible with, for example, CMOS technology. Also, the second novelty or work is that, as far as we know, for the first time, we construct a device where the antiferromagnetic element is downscaled in the micrometer range. So usually, this is the first set of devices that I will show you. The devices consist of a whole bar that is down by platinum. Here you can see a 3D scheme, or another heavy metal. And in the middle of the whole bar, we pattern the antiferromagnet in a pillar shape with a thickness of between 4 and 10 nanometers and diameters of 6 and 10 microns. So the first experiments that we performed with antiferromagnets were in platinum manganese. So all the results I'm going to show you, it's a bilayer of platinum 5 nanometers thickness and platinum manganese 6 nanometers thickness, and 4 microns of diameter of the antiferromagnetic element. And the devices were the whole bar that is formed by the platinum heavy metal, and in the middle, the platinum manganese pillar. So in these devices, we also use a second harmonic detection technique that has been previously used in other antiferromagnets, like the copper manganese arsenide, where, for example, between the terminals A prime, we apply a small AC current with an amplitude of 0.5 milliamps and frequency of 501 hertz. And this small AC current will generate by a nonlinear effect, a second harmonic voltage between the terminals BP prime that is related to the direction of the Snell vector of the ferromagnet. So we use this structure and this reading method to see how the second harmonic voltage or the Snell vector or the antiferromagnetic state change when different current pulses are applied between terminals BP prime in different directions, different amplitudes. And as you can see, after applying several pulses for all the cases that we try, that is for amplitude currents between 2 and 10 milliamps, we see a swing of the output voltage between two states. And that voltage difference increases when we increase the amplitude of the current pulse. So we have an effective switching of the antiferromagnetic state. To understand the origin of this switching effect, what we did is another experiment where we start applying a current pulse with a very high current, the maximum that we can apply in our experiment, that is 10 milliamps. And then after that, we reverse the direction of the pulse and start progressively increase the amplitude of the current pulse, in this case, until 2 milliamps. Once we arrive to a maximum amplitude current, 2 milliamps in the case I'm pointing, then we start to reduce again the amplitude until we arrive to 0, and then we reverse the direction of the pulse and arrive in the other direction to the maximum amplitude. And then we close the loop, but in this case, increasing the maximum current, amplitude current, in this case, from 2 milliamps to 3 milliamps. And then we repeat this loop cycle for 3, 4, 5, 6, 8, and 10 milliamps. And as you can see, the output voltage progressively increase when we apply these current pulses, suggesting that the switching mechanism in the antiferromagnet take place by nucleating domains. And once the domain is nucleated, that's just depend on the amplitude and direction of the current pulse. So we want to change that micromagnetic state, we need to change the direction of the amplitude current of the writing pulse. If you want some details, you can take a look to this very nice paper that we published, where some simulation performed by Professor Giovanni Finocchio will show also in a micromagnetic framework these micromagnetic states that I told you. Also, if we measure the voltage variation between the maximum current applied in both directions, we can see that as function of this maximum current, we see that progressive change that suggests that the switching of the antiferromagnet occurs through different metastable states. Another way to see this effect is if doing an asymmetric switching. So we fix the amplitude of the current pulses to 10 milliamps in the case I'm showing you, and we start to apply different number of pulses in each direction. And you can see that independently of the number of pulses that we apply, always we reach very fast a constant value. We reach a plateau. This is because the micromagnetic state, the state of the antiferromagnet is just set by the current and the amplitude of the current pulse and the direction. Once it's set, if you want to change that state, you need to change the amplitude of the current. So that's analogous if we measure these current loops that I showed you before several times continuously. And as you can see, the output voltage always revisit the same value. So suggesting that this effect just happened by the change of the micromagnetic states of the antiferromagnet. And as very interesting remark, this device can work as two ways. Can be used as a digital memory if you fix the amplitude of the current pulse and just change the direction, or as analog resistance if you also change the amplitude current. And also it can be very useful and interesting, this device, for working as a synapse for neuromorphic computing. So before going to the second set of devices that I will show you in this talk, just comment that in the last years appear some works where they demonstrate that applying very large currents in the structures that most of the people is using in antiferromagnets, but without the antiferromagnetic element, can generate the heavy metal because of these large currents, signals that can be similar or hide the real behavior of the antiferromagnet. Here you can see some reference that you can consult and also some results that are very similar to the studies that very similar to the results that people obtain with antiferromagnets. So based on that, we try to construct a method or a device that in an ambiguous way we can detect the antiferromagnetic switching signals. So we propose a new kind of device where consists of two whole bars that has a long arm in common, and in one of the devices we pattern the antiferromagnet as a shape pillar with a shape of a pillar in the middle of one of the crosses. Another one is just formed by the heavy metal, in this case platinum. And we use this kind of devices in other antiferromagnetic material that is non-collinear iridium manganese free. So it has some uncompensated spins that can increase the reading signal. So the novelty of this system is that if when you apply a writing pulse of high current and any signals generated in the platinum, if you measure the output voltage between terminals 2 and 3 or terminals 6 and 5, these signals generated by the platinum will be removed. And for example, if we apply just current pulses in 180 degrees between terminals 2 and 6, we will see in principle just the effects on the iridium manganese. Also, and the second advantage is that because we have two equal devices, but one with the antiferromagnetic element and the other one without, we can also do reference measurements and compare the switching signals between the reference sample, just the heavy metal, and the complete device with the antiferromagnet. So doing this experiment, just one other thing, that is where we measure the output voltage by AMR reading, applying a small current of 100 microamps in between the directions, in between the terminals 1 and 4, and then reading always the output voltage between terminals 2 and 3. So this device allows to make 2 or 3 different switching schemes that are 180 degrees switching, that is applying current pulses between terminals 2 and 6 in different polarities, or 3 and 5 if we want to measure the reference platinum. And this result corresponds when we apply current pulses of 20 milliamps. So you can see that the main result here, we have a complete switching of the output voltage always when we apply the current pulses between terminals 2 and 6. However, when we apply the pulses in between terminals 3 and 5, we have almost zero signal. So in an ambiguous way, we can ensure this device that the switching is related to the iridium manganese. Just one note is that the switching in this device is different than the previous devices that I was showing you. This case is because the minimum density current that we got switching in the previous devices was 2 megaamps per square centimeter, and we just were changing the metastable state of the antiferromagnet. In this case, we are applying density currents around 40 megaamps per square centimeter, because this iridium manganese pillar is 10 nanometers thickness, but the diameter is 6 microns. So in this case, the switching takes place by the effective domain wall motion of the antiferromagnetic domains. Also, we can repeat these switching experiments applying a 90-degree switching schema with the same amplitude. In these devices, the threshold current, if you are interested, was 18 milliamps. So these 90 degrees consist of applying a current pulse in the direction of the common arm between the two whole bars, and then the second pulse, the different direction of the second pulse, is just in the iridium manganese pillar, terminal 6 and 2, or in the reference device between terminals 5 and 3. And as you can see, when we apply the current pulse just in the iridium manganese in 90 degrees switching scheme, we have big switching. We can see how the voltage output swings between two states with this domain wall motion that I commented in the previous case. And when we do that, applying also the current pulse just in the platinum part, when the current pulse just goes through the whole bar that is from platinum, we don't see any change in the signal, what is consistent with the previous results. You can see that there is a small change when we apply the current in the long arm, but it makes sense because this current pulse is passing through the iridium manganese also. So we have some domain wall movement and relaxation process that generates a small signal, but never compare it with the case when all the pulses just pass through the iridium manganese. So in conclusion, I show you an effective switching of the antiferromagnetic state of metallic antiferromagnets, in particular in two materials, in platinum manganese and iridium manganese free. And that was very interesting because not just we use two techniques, a technique that is very sensitive to detect the deflection of the Snell vector in platinum manganese, but also a technique that allow us a good platform to distinguish signals between the antiferromagnet and the heavy metal layer. But also I show you that there are two switching processes. One allows the current density in more or less 2 megaamps per square centimeter in the case of platinum manganese, that is related to the change of the micromagnetic state of the antiferromagnet. And the most studied case, that is the case of the iridium manganese free devices that I show you, where the switching is related to domain wall motion and the density current, the whole threshold density current we need to move the domains. In this case, is around 40 megaamps per square centimeter. One of the good points of these materials is that they are fully compatible with CMOS technology, so we can combine them with transistors and current technology that foundries are working on now. And both cases, we downscale the antiferromagnetic element into the micrometer scale. Now we are working to try to go to the nanoscale and see if we see any difference. And finally, in the case of platinum manganese devices, you saw that this device can work as an analog memory if we change the amplitude and the direction of the current pulse. That can be very interesting for synapse, for working as a synapse for neuromorphic computing. Also, both devices can work as a memory, digital memory, just changing the current pulse and direction. Right. Thank you very much for attending to this talk, and I will be very happy to respond to any question that you have.